Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. Apollo 17, humanity's final journey to the moon, but not the end. Do you think we already know everything there is to know about the moon? Well, think again. In 1972, Apollo 17 took off with a brand new set of goals and cutting-edge technology, making it the final manned mission to the moon. But this wasn't just another landing, it completely changed our understanding of Earth's lunar neighbor. The astronauts drove the lunar rover into areas that had previously been off-limits, bringing back samples from the moon's surface and uncovering secrets hidden for billions of years. Apollo 17 gave us a history book of the moon, bringing us closer to understanding the true nature of the universe. But before we dive into the science, let's meet the three astronauts on Apollo 17, heroes, each with their own fascinating story. These weren't just astronauts, they were pioneers, each with a unique background, personality, and sense of mission. In December 1972, they embarked on a historic journey that would forever change space exploration. First up, Eugene Cernan, who became the last person to walk on the moon. That footprint he left on the lunar surface in the Taurus Littrov region is still there today, standing the test of time. But before this moment, Cernan had already lived a life full of extraordinary achievements. Born on March 14, 1934, in Chicago, Illinois, Cernan came from a humble family. His father was an architect, and his mother, a homemaker. From a young age, Cernan was fascinated by flight, showing a natural aptitude for math and physics in high school. He earned a degree in engineering from the University of Southern California and became a Navy pilot. By the time he joined NASA, Cernan had already logged nearly 5,000 flight hours as a top-tier Navy aviator. After Apollo 17, Cernan continued to be a prominent figure in aerospace, working with tech companies and promoting space exploration. Even after retiring, he remained passionate about educating the public about space. Sadly, Cernan passed away on January 16, 2017, at the age of 82. As the last man on the moon, his legacy is forever entwined with the history of human space exploration. Next, let's talk about Harrison Schmitt, the only scientist astronaut on Apollo 17. Not only was Schmitt a pilot on the mission, but he was also a trained geologist. On the moon, he conducted a series of crucial experiments and geological surveys, helping us understand the moon's composition better than ever before. Schmitt, born on July 3, 1935, in Albuquerque, New Mexico, had a deep interest in geology from a young age. He earned a PhD in geology from Harvard University and worked for the U.S. Geological Survey before joining NASA. His scientific background added immense value to the Apollo 17 mission. Can you imagine a geologist walking on the moon? It's like the holy grail for someone in his field. Despite applying to NASA's astronaut program multiple times, Schmitt wasn't selected until 1965. Once on the mission, he made significant contributions, particularly in sampling lunar material. He even named one of the samples the moon's birthday gift, a critical geological rock sample that was brought back to Earth to help scientists piece together the moon's history. After the mission, Schmitt not only continued working with NASA but became the only scientist to ever collect lunar samples. Later, he transitioned into a career in politics, becoming a U.S. Senator from New Mexico in 1983, where he championed science and technology policy. Schmitt's unique background and his role as the moon's scientist made him a legend in the space history books. Last but not least, we have Ronald Evans, the command module pilot for Apollo 17. Although Evans didn't walk on the moon, his role was absolutely critical. While Cernan and Schmitt were on the lunar surface, Evans was flying the command module, ensuring everything went smoothly in lunar orbit. Born on November 10, 1933, in St. Louis, Missouri, Evans grew up in a modest family but was instilled with a strong educational foundation. Like many Apollo astronauts, Evans was a Navy pilot, and before joining NASA, he had already completed thousands of flight hours. During Apollo 17, Evans operated the spacecraft during its lunar orbit, performing essential tasks like docking with the lunar lander and maintaining communication with Cernan and Schmitt. He once humorously remarked that while he didn't step on the gas, he was, in a way, still driving the whole mission from orbit. The astronauts would joke about this, but Evans' work was crucial to the mission's success. After Apollo 17, Evans continued to work for NASA, contributing to several other space projects. He retired in 1977, but remained involved in aerospace work until his death in 1990, at the age of 56. Though Evans never set foot on the Moon, his contributions were essential, and his legacy is forever linked to the success of Apollo 17. So, whether on the surface or in orbit, these three astronauts made Apollo 17 a mission that forever shaped our understanding of space and our place in it. Apollo 17 launched on December 7, 1972, at 12:55 p.m., when the mighty engines of the Saturn V rocket roared to life, tearing through the Florida skies and into space. This was the final launch of the Apollo program, and the Saturn rocket's last hurrah. Once the rocket left Earth's atmosphere, the three astronauts on board quickly entered space, and the command module, Challenger, detached successfully and entered its designated orbit. The first phase of the flight was all about getting everything in sync. The astronauts completed spacecraft docking, ensuring all the equipment needed for the mission was functioning smoothly. Then it was off to the Moon, a 72-hour journey with precise course corrections along the way, and the spacecraft successfully entered lunar orbit. This mission followed the classic Earth-to-Moon trajectory, taking about 72 hours. During this time, the astronauts didn't just sit back and relax, they had to constantly adjust their spacecraft's orbit and check each system to ensure everything was up to snuff. They kept in constant communication with mission control to make sure everything was safe and on track. Unlike previous Apollo missions, Apollo 17 had a bit more on its plate. Every orbital adjustment was crucial, especially as they approached the Moon's gravity. Getting that flight path and navigation spot on was essential. As they entered the Moon's gravitational influence, the astronauts began preparing to separate the lunar module for the Moon landing. On December 11, after a few days in space, Challenger successfully entered lunar orbit. Eugene, Cernan and Harrison Schmitt climbed into the lunar module, ready to begin their historic mission on the lunar surface. Meanwhile, Ronald Evans remained in the command module, keeping the spacecraft operational and monitoring the mission. The lunar landing site chosen for Apollo 17 was the Taurus-Littrow Valley, a scientifically valuable area believed to hold rich samples that could reveal the Moon's origins and evolution. As they prepared to land, the astronauts faced some tricky maneuvers. The landing required precise orbital adjustments and real-time data analysis from the ground. But on December 11, Cernan and Schmitt successfully touched down on the Moon, marking Apollo 17's first successful landing. Once on the Moon, Cernan and Schmitt didn't waste any time. They weren't just going to stroll around, they had work to do. In addition to setting up scientific instruments, they used the lunar rover to explore much larger areas, marking the first time a rover was used on the Moon, and dramatically expanding their range of exploration. Over the course of 3 moonwalks, they drove the rover about 35.7 kilometers, collecting a vast amount of lunar rock samples. But their work didn't stop there. They also conducted some unique experiments, including geological surveys and radiation measurements. After 16 hours of hard work, they wrapped up their surface tasks and prepared to head back to the lunar module. Once they completed their surface work, Cernan and Schmitt successfully returned to the lunar module. On December 14, the lunar module docked with the command module, and the astronauts reunited. At this point, the spacecraft was ready to start the journey back to Earth. The lunar rover, now left behind on the Moon, would forever remain there as a silent witness to Apollo 17. The 3 astronauts continued to adjust the spacecraft's trajectory, ensuring a safe return to Earth. By December 19, after a few more orbital corrections, Challenger re-entered Earth's atmosphere. The astronauts executed a flawless re-entry, and a few minutes later, parachutes deployed, bringing them gently to the Pacific Ocean. Waiting for them in the ocean was the U.S. Navy's rescue fleet. After landing about 300 kilometers off the coast in a designated rescue zone, the astronauts were quickly retrieved and brought back to the recovery ship. Their mission was complete. The secrets of the Moon were safely back on Earth. This wasn't just a victory for the astronauts, it was a triumph for humanity's space exploration history. On December 19, 1972, the astronauts were welcomed back as heroes. Although this marked the end of the Apollo program, their successful return made the entire world proud. Cernan, Schmitt, and Evans' names would forever be etched into the history of human space exploration. The mission lasted 12 days, 13 hours, and saw the astronauts complete numerous scientific experiments. They also returned with 110 kilograms of lunar samples, which would provide valuable data on the Moon's origin, evolution, and geological structure. But of course, the success of this mission wasn't just about the samples. There was a remarkable scientific journey happening right on the lunar surface. This mission had a unique twist that set it apart from the others. Harrison Schmitt, the geologist, became the only scientist astronaut in the entire Apollo program. His presence made this mission extraordinary. Not only was he an astronaut, but he was also a genuine scientist, bringing a wealth of lunar expertise to the table as he set out to conduct real geological research on the Moon. Cernan and Schmitt had a clear mission: to conduct extensive geological surveys using the lunar rover, collect lunar rock samples, and perform a series of unprecedented experiments. The chosen landing site, Taurus Littrow, was rich in scientific potential, believed to hold crucial clues about the Moon's history. On the morning of December 11, Cernan and Schmitt drove the lunar rover for the first time on the Moon. They weren't just collecting samples, they were exploring an alien world, trying to unravel the mysteries of the Moon's past, present, and future. Their first stop was a place known as the Rock Zone, an area with rich rock layers that captivated their attention. Over the course of about 5.4 kilometers, they collected their first batch of rock samples. These samples would go on to play a crucial role in understanding the Moon's formation and geological history. The next day, December 12, they geared up for another adventure. This time, they drove 9.2 kilometers to the South Valley, one of the most challenging areas on the Moon. As the rover's wheels left marks in the gray lunar soil, they headed toward a region full of ancient geological records. Here, they conducted large-scale sampling and geological surveying. Each kilometer they covered was a major leap forward in lunar science. They also installed scientific instruments, such as radiation detectors and a laser reflector, which would continue to provide critical data for decades to come. By December 13, the astronauts had fully adapted to the lunar environment, and the lunar rover had become their trusted exploration tool. That day, they drove another 7.4 kilometers to an area called the North Valley, rich with lunar rocks and deposits. Cernan and Schmitt continued their sampling and delved deeper into the Moon's geological layers. They closely examined rock strata that held records of different geological periods in the Moon's history. This data, along with detailed notes on the terrain and surface features, helped scientists piece together the Moon's evolution. Every rock and inch of terrain on the Moon was telling a story. The work of Apollo 17 would help scientists understand how the Moon evolved, revealing its close relationship with Earth. Apollo 17 wasn't just about collecting rocks and soil, it included a number of complex scientific experiments, such as testing the physical and chemical properties of the lunar soil. Cernan and Schmitt used specialized equipment to test the soil's hardness, composition, and structure. These tests didn't just reveal the nature of the Moon's soil, they also provided crucial data for future lunar base construction. Then, there was the radiation experiment. With no atmosphere on the Moon to shield from harmful radiation, understanding the lunar radiation environment was vital. The astronauts placed radiation detectors at various locations, gathering valuable data on radiation intensity, data that's still useful today in helping protect astronauts from space radiation. And let's not forget the laser reflector, a highlight of this mission. With this instrument, scientists could measure the distance between Earth and the Moon with remarkable precision. This experiment's data continues to be used to study subtle changes in the Moon's orbit and Earth-Moon dynamics. So, Apollo 17 wasn't just a mission to the Moon, it was a scientific treasure hunt that continues to impact space research to this day. In this mission, Cernan and Schmitt worked tirelessly for 16 hours, driving the lunar rover for a total of 35.7 kilometers and collecting a treasure trove of lunar samples, rocks, soil, and other geological materials. Behind every rock they collected was a piece of the moon's history, and every experiment they ran brought us one step closer to unraveling the mysteries of the universe. One of Apollo 17's biggest contributions was the moon samples it brought back. Cernan and Schmitt collected 110 kilograms of rocks and soil from the lunar surface, providing a deep dive into the moon's composition and offering essential clues about the formation of the moon and even the Earth. These samples didn't just enrich our knowledge about the moon, they opened a whole new chapter in planetary science. Lunar rocks, uncovering the moon's geological past. The lunar sampling site chosen for Apollo 17 was the Taurus Littrov region, a geologically rich area believed to hold the key to understanding the moon's early history. Cernan and Schmitt collected rocks like high-calcium pyroxene and lunar basalt, revealing volcanic activity on the moon's surface and a layered lunar crust. This discovery not only deepened our understanding of the moon's structure but also gave us fresh perspectives on Earth's own formation and planetary evolution. From these rocks, scientists concluded that the formation of the moon is closely tied to Earth's own formation. The moon isn't just Earth's companion, its history helps us understand the processes that shaped our planet. The Apollo 17 samples became a cornerstone for planetary science, providing a foundation for future studies of other planets and moons. Moon dust, paving the way for future lunar bases. In addition to rocks, Apollo 17 brought back a large amount of lunar soil, also known as regolith. Unlike Earth's sand, lunar soil is composed of tiny, sharp particles of dust, which pose a health risk to astronauts. But despite its dangers, studying lunar soil provides crucial insights into building future lunar bases and utilizing the moon's resources. Scientists discovered that the lunar soil contains high amounts of oxides, particularly oxygen. This finding has major implications for future lunar resource extraction, as oxygen could be used to sustain lunar bases. Additionally, hydrogen and helium, found in lunar soil, could be extracted to power energy systems and life support on the moon. The study of lunar soil also spurred the development of heat-resistant and radiation-resistant building materials. These materials, designed for use on the moon, could one day be applied to extreme environments on Earth, like in space missions or nuclear facilities. Radiation experiment, protecting astronauts' health. The moon, lacking Earth's protective atmosphere, is bombarded with higher levels of radiation. Apollo 17's astronauts didn't just collect rocks, they also deployed a radiation detector, gathering vital data for the long-term health of astronauts in space. Apollo 17's radiation experiments helped scientists measure the moon's radiation levels with precision. This data is crucial for understanding the effects of deep space radiation, especially for future missions to Mars. Though the moon mission was brief, it provided essential data on radiation protection for astronauts, laying the groundwork for long-duration space travel. These experiments contributed significantly to the development of radiation protection technologies. By understanding the intensity of lunar surface radiation, scientists have been able to design better protective suits and develop more effective shielding materials to ensure astronaut health on future missions. Laser reflector, measuring the Earth-Moon distance with precision. One of Apollo 17's standout experiments was the deployment of a laser reflector on the moon. This device, placed on the lunar surface, was used to measure the distance between Earth and the moon with unprecedented accuracy. By firing a laser and timing how long it takes for the light to bounce back, scientists could calculate the Earth-Moon distance to a fraction of a second. Long-term impact of the laser reflector experiment. The laser reflector didn't just measure the Earth-Moon distance, it laid the groundwork for modern satellite positioning systems and deep space exploration. This technology helped establish the foundation for precise distance measurement techniques, which are now essential for navigation and exploration on Earth and beyond. The experiment also had far-reaching implications for lunar orbital studies. By monitoring tiny changes in the moon's orbit, scientists can now understand the subtle dynamics of its movement and predict future changes. This data is invaluable for deep space navigation, providing essential guidance for future interplanetary missions. Lunar resource development. The moon as a mining colony. Can you imagine a mining base on the moon? Apollo 17 not only brought back data about the physical properties of the moon's surface but also provided key insights into lunar resource utilization. Water ice, minerals, and helium-3 resources that could fuel future deep space exploration and energy needs are all found on the Moon. Lunar resource exploration, helium-3 and water ice scientists discovered that the Moon's surface contains abundant helium-3, a rare and potentially valuable resource for nuclear fusion. Extracting helium-3 could provide nearly pollution-free energy, offering a revolutionary solution to Earth's growing energy crisis. In addition, the Moon's water ice is a game-changer for lunar base construction. Water ice not only provides a vital source of water for astronauts, but it can also be broken down into oxygen and hydrogen, providing essential gases for life support systems and rocket fuel. From space to Earth, the technological ripple effect. Apollo 17 wasn't just about lunar exploration, it had far-reaching technological and scientific impacts that extended well beyond the Moon. The mission's samples and data not only advanced planetary science and space engineering but also spurred technological innovations back on Earth. Advances in materials science. The study of the lunar soil and rocks collected by Apollo 17 led to breakthroughs in materials science. Researchers gained new insights into high-temperature materials, radiation-resistant materials, and more. These discoveries have influenced spacecraft design and have been applied to high-performance engines, extreme temperature materials, and industrial uses on Earth. Environmental monitoring and disaster warning. The radiation data collected by Apollo 17 also contributed to advancements in environmental monitoring technology. The techniques used to study lunar radiation have been adapted to track nuclear radiation and have applications in monitoring climate change and providing disaster warnings. Apollo 17, a stepping stone to the future. The scientific breakthroughs and technological advancements achieved by Apollo 17 continue to shape our understanding of the Moon, space travel, and resource utilization. The legacy of this mission paves the way for future space exploration, from establishing lunar bases to embarking on deep space missions. The Moon is just the beginning. With plans like Artemis II, humanity's return to the Moon on the horizon, we are setting our sights on Mars, the next great frontier. These missions are no longer just the dreams of scientists, they're becoming tangible goals for future generations. Each breakthrough, each step forward, proves that humanity has never stopped reaching for the stars. Our exploration spirit is driven by an insatiable curiosity about the unknown. Whether it's the edges of our blue planet or the vastness of the cosmos, every step forward challenges the limits of what we know. As we navigate the stars, our eyes remain fixed on a future once thought unreachable, where the impossible becomes possible. The journey is not just about exploring space, it's about expanding our understanding of who we are and what we are capable of. Every conversation with the cosmos reshapes the meaning of our civilization. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.